Evening, everyone. Welcome to the fourth live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So in today's session, we will first have a recap for the last live session that was for week 3 content, a quick recap, and then we'll look through the things covered in the week 4 content. So week 4 content that we'll discuss today will be about chemical admixtures and mineral admixtures, which is divided into following subsections for today's discussion. First, we'll start with chemical admixture, where we'll talk about plasticizers, retarders and accelerators, air training agents, viscosity modifier, shrinkage reducing admixtures and waterproofing agents. Then we'll discuss basics about mineral admixture. We'll go through the characterization of SCMs, Pozzolanic assessment testing methods, hydration of pozzolans, and finally effect of SCMs on fresh, hardened, and durability properties. In between, I will have questions related to the content. So in total, there will be around 23 questions today. So which are oriented towards application of theory, whatever we'll go through. Finally, we'll conclude the session and I will try to address any other queries post discussion. So last week we concluded the third week of the course where we started with the discussion on characterization of aggregates used in concrete based on size, shape and surface texture. As per IS 383 guideline, we say that aggregates used in concrete are classified into two broad categories, coarse aggregate and fine aggregate based on their size. Then now how to judge the size of aggregate? We saw standard using standard sieves which have square openings of different size. So by passing an aggregate batch through the set of different sieves that are defined by a standard from larger to finer, we do sieve analysis of aggregate. Then we talked about two quantitative measures based on sieve analysis. These are fineness modulus, which is used for fine aggregates, and there is surface modulus, which is used to calculate the net surface area of a aggregate batch. We had a quick overview of classification of aggregates based on shape and surface texture. We discussed about packing density of aggregate in a single-sized and multi-sized system. We derived how void percent in a multi-sized aggregate system depends upon aggregate proportioning and saw its relationship with packing density. And finally, we talked about properties of aggregate, wherein we saw physical properties of aggregates like sieve analysis and water absorption, and we discussed about mechanical properties like crushing value, impact value, and abrasion value. And we had a very quick overview of chemical properties like alkali aggregate reaction and soundness. So this was for the last week content. Now, if you go to the first live session that we had, we talked about composition of concrete, for which we saw one equation, and we saw that admixture is an optional entity in that equation. Okay, so these admixtures are added as an additional part as a replacement to main components like water or binding system. Okay, so our today's discussion will be about understanding this final component of the equations, the equation that we wrote in the week 1 session. Okay. Now, though we say that admixtures are an optional entity, they are an additional part, but in reality, in many countries, for preparing a concrete mixture, aggregate use of admixture, like preparing a concrete mixture without using admixture is exceptional. Okay, so it is like very commonly used, and it is not anymore an optional entity. It is a must entity in the concrete. Yes, there's which query you raised last week?
It's the ranges you mentioned for the finest formulas. I asked where it is mentioned exactly. I mean, which
Can we
standard?
see that query at the end of the session if it is
Yeah,
okay for
sure.
you?
Yeah, sure. Fine. Thank you.
Okay. So yeah. So, as I was saying, use of admixtures is said to be an optional entity, but nowadays preparing a concrete mixture without admixture is exceptional. Okay, it has become a must-needed and added entity. Why so? Because they can impart considerable physical and economic benefits to concreting. Now, how they impart this beneficial effect to concrete? By enhancing the workability of concrete, which is useful for making pumpable concrete in large construction project. Admixtures can increase the strength and durability by replacing water or cement to allow making a denser concrete. They can help us make suitable special purpose concrete which may be used for urgent repair in hot weather or in mass concreting, and they make concrete cost effective and sustainable. Although these admixtures are not cheap, but they can still result in indirect saving like reducing cement content without compromising strength, lowering the total construction cost, or lowering the cost of labor. Okay, so because of these key reasons, use of admixtures has become very important in concreting. Now, admixtures are categorized in two types: chemical admixtures and mineral admixtures. So, first we'll talk about chemical admixtures. So, how we define a chemical admixture? So, these are chemical products which are added in concrete in quantities not more than 5% by mass of cement during mixing or placing of concrete, prior to placing of concrete, to achieve specific modulation or modification in normal concrete. So, in simple terms, if I say, chemical admixtures are the chemicals which are added in very small quantities during concreting to modify the fresh properties of concrete as per our need. Okay. So these chemical admixtures, they are classified into different categories based on their function in concrete. What are these categories? So the first category is adsorption on cement surface to cause dispersions. Okay, so admixtures which are responsible for dispersion, they are known as plasticizers and super plasticizers. Now, those admixtures which will interact during hydration, these are known as accelerators and retarders. Those will who will affect the surface tension of water will are known as air entraining agent. Those affecting the rheology of cement paste are known as viscosity modifiers, and those which are added as a special agents in hardened concrete are known as corrosion inhibitors and water repellent admixtures. Okay, now these admixtures, they are generally present in liquid form so that they can rapidly disperse in uniform manner during mixing. Okay, so when you will spot a chemical admixture, you will see it is in a liquid form and it is added in very small quantity during concreting. So we'll go one by one through all these different categories of admixture and we'll understand how they function and why they function like that. Okay, so first let's see dispersing admixtures, which includes plasticizers and superplasticizers. So as the name suggests, dispersing admixtures are used in concrete to improve the workability of concrete by reducing water content without compromising the consistency. Okay, so as we said in the start, admixtures are alternative to basic component. So here, dispersing admixtures are those which are added as a replacement of water. And even though they are reducing the water content in concrete, they are still enhancing the workability of concrete. How it is possible? Because these admixture, they tend to disperse the cement grain from each other. Okay, and in this process they lower the water required to achieve uh, a level of workability that we demand. Okay, how they disperse cement particles, so that we'll see shortly when we'll discuss about mechanism of dispersing admixtures. Okay, now dispersing admixtures are of two categories. These are plasticizers and super plasticizers. So plasticizers, they are also known as water reducing admixtures, and super plasticizers are high range water reducing admixtures. Okay, now in chemical admixtures, 60% of the chemical admixtures that are used in concreting are dispersion admixtures. Okay, so these are one of the most commonly used admixtures in concrete. So if we talk about first about plasticizers or water reducing agents, They improve workability of concrete by reducing the water demand. Okay, that we have already seen from the general definition of admixtures. And what are their key properties? They can reduce the water content by 5 to 15%. So suppose I required 400 kg of water. Instead of 400, I can use 360, 320 to 360 kg of water to achieve a standard level of slump workability that I want for concrete. Okay, so in this way, I'm replacing the water by a very small quantity of SP, say 1% or 2% addition of SP. I'm reducing water by 5 to 15%, and I'm achieving the same level of workability from the concrete. So this is the power of a plasticizer. They reduce the water content required for achieving a level of workability. They can improve the strength. How? Because we are reducing the water content, we are reducing the W by C ratio, and if we are reducing the water to cement ratio, we will increase the strength of concrete. They can give better workability. Okay, instead of decreasing the water content, if we maintain the same water content level and add SP, we can increase the workability of concrete also. And they also reduce segregation and bleeding. Okay, so they improve the cohesion and uniformity in mixing. So if we have a very dry concrete, by addition of admixture of a plasticizer, we can reduce the chance of segregation in such concrete. Okay, so what are the commonly known plasticizers? These are lignosulfates, hydroxylate carboxylic acid, and polycarboxylates. So these are some of the common admixtures that are used as superplasticizers, and they are normally used in normal strength concrete, precast elements, and pavement, and they are suitable for moderate improvement in workability and strength. Now, after plasticizer, if we see about super plasticizers, or what they are commonly known as high range water reducing admixtures, so they provide much higher degree of water reduction than normal plasticizers, and they allow extremely fluid and high strength concrete. Okay, so what are the key features? So instead of 5 to 15% reduction in water content that we saw for plasticizers, which with super plasticizers we can go up to 15 to 40% reduction in water, uh, making concrete highly workable. Okay, so we can reduce water content by 15 to 40%, and we can maintain the same level of workability, or may increase the workability. Okay, they are used in self compacting properties. Okay, they produce flowable concrete that doesn't require compaction, as they impart very high level of workability. They are used in high strength and durability concrete, for which are essential for high performance concrete, and they promote better compaction in concrete. By making concrete workable, they reduce the air voids that are there inside concrete while pouring it inside the formwork, which leads to a creation of dense and impermeable concrete. Okay, what are the commonly known superplasticizers? These are sulfonated melamine formaldehyde, sulfonated naphthalene formaldehyde, and modified polycarboxylates. So these are commonly used superplasticizers as a chemical admixture in concrete, and their application is in high strength concreting and self compacting concrete, precast element, pumping concrete, and mass concreting. Okay, now what is the science behind working of these chemical admixtures, these plasticizers, or we can say chemistry behind these chemicals, which make them act as a dispersing agents? So both plasticizers and super plasticizers, they belong to dispersant family, and these chemicals, they are composed of a surfactant, which is also known as water reducers, which is composed of long chain organic molecule having a hydrophilic head, and a hydrophobic chain. Okay, so the hydrophilic head which is present in this plasticizers, they are water attracting. Okay, what are these hydrophilic heads? These are the acid group, the sulfonate group, or the amine group. Okay, and they are attached to long chain of non-polar hydrocarbon hydrophobic chain. So these are hydrocarbon chain which is non-polar, and they are water repelling. Okay, so combination of these two elements in a plasticizer make them act as a dispersant. Okay, so So, and they dispersed cement grain either by electrostatic dispersion or steric hindrance. Okay, there are two mechanisms by which they cause dispersion. Okay, so initially, when cement grains are dispersed, the water present for workability is more, and over time, they increase the workability. So, initially, when we add a plasticizer to a concrete system, they disperse the cement grains from each other, due to which the water that is present inside concrete is now available for workability. And over time, as the water is consumed, the electrostatic dispersion that was occurring due to the plasticizer, they diminish, and again the cement grains which are separated after hydration, they flocculate into final products and they densify the concrete. Okay, so in this slide, I have just shown you some structures of the superplasticizers that we listed a few slides ago, like here, common superplasticizers that we listed. So we have lignosulfates, we have sulfonated naphthalene formaldehyde, we have polycarboxylic ether, we have sulfonated manylyl formaldehyde. In all of them, you can see there is a long chain of hydrocarbon which is present. Okay, and there is a hydrophilic group attached to it. So here you can see the hydrophilic group is here. This is sulfonate group present here. Okay, there is this ether group uh, here, and there is again sulfonate group here. So these group are the hydrophilic ends, which are water loving, and this entire hydrophobic chain, which is water repelling in nature, and both of them combine to make a dispersant admixture. Now, how they disperse cement grain? Okay, so if we just see a simple cement plus water system, my cement grains are not separated. They are naturally present in the form of a cluster, like you can see here. Okay, these are my cement grains, which are naturally present in the form of cluster, like a flock. Okay, and when they are present in the form of cluster, they can trap water inside them. Okay, now why is this flock formation happening? Because of van der Waals force of attraction between cement grains. Okay, so when we talk about a cement particle, there can be two things: either there can be attraction or there can be repulsion between grains. Okay, so in cement, due to the presence of free valencies in calcium, aluminium, and silica atoms on the cement grain can be cationic in nature. That means they can carry some positive charge. Okay, and if they hold very slight positive charge on them, two cement grain will try to repel each other because of the presence of this positive charge. However, this repulsion force due to the cationic nature of cement grain is very weak, and thus there is van der Waals force of attraction between the cement grains which dominates, and they create the flock of different grains that merge together. Okay, now due to this flock activity, what happens, there is water trapped inside a cement grain, and we know, since water is a surface phenomena, hydration is a surface phenomena, this entire water which is trapped, it is actually a loss for the workability, because hydration will slowly proceed on the surface, and due to this the entire water is not getting consumed effectively. Now, what happens when we add superplasticizers? So superplasticizer has the polar group which is water loving, or we say hydrophilic in nature, and there is non-polar hydrocarbon chain which is hydrophobic, like you can see here. This is the polar group which is water loving, and this is a non-polar group, okay, which is my hydrophobic side chain. Okay, now what happens when these superplasticizers are added in concrete? They cover the cement grain such that my non-polar group, they will cover the cement grain, while my polar group will disperse outward in water. So you can see here, this is my cement grain, the non-polar group, it is covering the cement grain, and my polar group is dispersing out. Okay, and since this polar group is water loving, they will repel, they will these two groups, they will repel each other, and they will release the free water which is present between the which is trapped between a cement grain flocks. And as this water is freed up, they become available for enhancing the workability of concrete. Okay, so in this way, this plasticizer system work as a dispersing agent. Okay, so polar group is surrounding the cement grain, non-polar group is surrounding the cement grains, and polar group is moving the cement grains away from each other, and they are releasing the trapped water from between. Now, in the last slide, we saw there are two reasons by which dispersion works, either by steric hindrance, okay, that we saw in this slide, where these groups were repelling each other and separating cement grains, and there is electrostatic repulsion also, which is also there, which can impart dispersing nature. So, what is electrostatic repulsion? It is based on the concept of zeta potential. Okay, so zeta potential is an electric charge that exists on a tiny particle suspended in liquid, like cement in water. So we saw cement carries a very small charge. It can be positive or negative depending upon what is the composition of that cement grain. Now it controls how these particles interact, whether they will repel, attract, or clump together. Okay, so if a cement grain has very high zeta potential, they will repel each other. Okay, because of repulsion between like charges. If they have very low zeta potential, they will attract each other in a kind of flock. Okay, so we saw initially cement grain has very small charge over them, so they have very low zeta potential, due to which they were creating flock. However, due to addition of admixtures, these dispersing agents, they can increase the charge density over cement grain, and they can make cement grain go from low zeta potential to high zeta potential. Okay, so the negative charge imparted by water reducers on the surface of cement grain, they repel each other, and in this way it can cause dispersion. Okay, so either it can be due to static hindrance due to site change, or either it can be due to the negative charge imparted by the superplasticizer, which can cause repulsion. Okay, so this was all about how a water reducing admixture work, and this slide just summarizes the action of water reducing admixture. So this is a very important slide for everyone to understand the crux of what is the need of water reducing admixture. Suppose we have a concrete whose compressive strength is known to us, whose workability is known to us, and if we are using water reducing admixture, if we are reducing the water content, okay, and so and we are maintaining the same level of workability, so what is happening, our workability remains the same, but since we are reducing the water content, we are reducing the w by c ratio, and in this way we can increase the strength of concrete. So this is one of the application of water reducing admixture, to maintain the workability and increase the strength. Now, if by addition of water reducing admixture I am reducing both cement and water, so what I am doing, I am keeping the W by C ratio same. So I am keeping the compressive strength same, I am keeping the workability same. But I have now decreased the cost of concrete, since I have reduced the content of cement required to make the concrete. This is the second application of water reducing admixture. So here we reduced water, here we reduced both cement and water. Here in the third application, water and cement are the same, but we are adding WRA in addition to that. So what we are doing, we are increasing the workability of concrete, but since water and cement content are the same, my W by C ratio is the same, so my compressive strength is the same. Okay, so this is the third application of water reducing admixture. Either I can increase the compressive strength and maintain workability, either I can maintain the compressive strength and increase workability, or I can maintain both compressive strength and workability and decrease the cost of the construction. Okay, so in this way we can use water reducing admixture in different ways. Okay, now based on the discussion of these water reducing admixtures, just try to answer these three simple questions. And in the meantime, if you have any doubts regarding the discussion that we had till now, you can ask. So in this section, it is very important for you to understand how a dispersing admixture is working, why they are causing cement grains to disperse, how they are reducing the water demand, how they are increasing the workability, and finally this slide. This slide is very important. So if you can understand this slide, the entire discussion will be clear to you. So just think, if you have any doubts, try to ask. And those who don't have any doubt, just try to answer these three questions. So can anyone tell me the answer for question number one? What people are saying: Vic apparatus, slump retention, compressive strength. Okay, we'll see. So the correct answer for first question will be slump retention test. Why? Because we are talking about enhancing the workability of concrete. Okay, most appropriate measure for maintaining workability over time. Okay, so since we are talking about workability over time, okay, so we need to check the slump of concrete. Okay, so initially at 0 minute, what was the slump? Slump means the spread of concrete or flowability of concrete. So at 0 minute, what is the flowability of concrete? We'll see. Then after 30 minutes, we'll again check the flowability. Then after 1 hour, we will again check the flowability. Okay, so generally on site, when we talk about a flowable concrete, we require a slump of around 150 to 200 mm. Okay, so without using admixtures, what will happen? Initially, you won't get that high slump in normal concrete. A maximum slump you can get is 50 to 75 mm. However, on site there can be need for transportation and pumping, where using such low slump will make pouring of concrete very difficult, or compaction of concrete very difficult. So when we at superplastic, initially we have a very high slump, 150 to 200 mm, but we need to check during transportation, like after 1 hour, whether it is able to maintain that slump or not. Okay, and how much it is maintaining. So based on that, we can modify the dosage of super plasticizers that we are adding. Like we added 1%, is it enough to maintain a workability of 150 mm after 1 hour or not? Okay, so for that we do slump retention test. Okay, question number two: how does the molecular weight of polycarboxylate superplastic affect its performance? So think about the two mechanism of dispersion we talked. One was steric hindrance and one was electrostatic repulsion. Steric repulsion or hindrance, anything you can say. Okay, for question number two, correct answer will be A. Because if I have a higher molecular weight polycarboxylate, then it means that I have better steric repulsion. High molecular weight will come when there will be a longer chain of hydrocarbon in my plasticizer. And the longer is the hydrocarbon chain in my plasticizer, the better will be the steric repulsion due to the plasticizer. And stronger is the repulsions, longer will be the slump retention. Okay, so as we said in the definition of these plasticizers, over time their effectiveness reduce. Okay, and eventually the cement hydrated cement particles will flock again. Okay, but if the steric repulsion effect is stronger initially, then it will take it more time to reduce the effectiveness, and thus it will be able to maintain slump for a longer time. Question number three: what happens if we add too much super plasticizer to concrete? So suppose I needed 1% super plasticizer for getting a workability of 150 mm. Now what will happen if I add 2% instead of 1%? Okay, so the correct answer is B. They will cause segregation and bleeding. So you will see that these chemical admixtures, they are very sensitive to dosage. Okay, if we want 1%, even if we had 1.1%, it will cause bleeding. What do you mean by bleeding? Bleeding will be like aggregates and cement paste, they will separate. Okay, so and that happens when we have too much water content in concrete. So if we add excess of super plasticizers, you will see that aggregates will separate and cement paste will separate when we will do compaction, and that will lead to bleeding of paste, and it will lead to segregation of aggregate system and paste system. Okay, so that's why it is very sensitive in terms of dosage. Okay, so this was about plasticizers and super plasticizers. Now, next we'll talk about set controlling admixtures, which include retarders and accelerators. So, as the name suggests, they control and manipulate the setting behavior of cement paste, which we can say eventually manipulates the setting behavior of concrete. Now, what is the basic mechanism of action of these admixtures? Okay, so they infer with the cement hydration reaction. Since they are manipulating the setting behavior of a cement paste, it can only be possible when they are intervening with the hydration reaction that is happening. Okay, now how they do that? So they the rate of dissolution cement grain during hydration is either speeded up or slowed down. Okay, so an accelerator, it will speed up the rate of dissolution rate of cement grain, and a retarder will slow down the dissolution rate of cement grain. Okay, so what type of set controller is needed depends upon the application. Okay, a retarder will delay the setting, whereas an accelerator will accelerate the setting process. Okay, so where we will use accelerator in cold weather concretings or in high early strength gain concrete, or where we need early removal of work, because here we want our concrete to set early, and where we require retarders in hot weather concreting or in concrete mixture which we want to remain workable for a longer time, or in concrete mixture where there are risk of cold joints. In such cases we want set our concrete to remain workable for a longer time, and thus we use a retarder. Now, what is this cold joint? So suppose we have a very long section of a concrete, okay, and we prepared 1 meter cube of concrete. We can prepare 1 meter cube of concrete at a time, and we were only able to pour up till half depth. Okay, now we'll go back again to the concreting plant and we'll prepare 1 meter cube concrete more to cover the second half. However, if my concrete is set before I pour the second half, then what will happen? There will be a cold joint that will be created at this new concrete and old concrete junction. Okay, and this joint, it can be a source for infiltration of aggressive ions from surrounding, or it can be a source for failure of concrete under loading. Okay, so this kind of joint that is creating due to delay in concrete pouring, these are known as cold joint. Okay, and to reduce the possibilities of such cold joint in large pour, we need to delay the setting of concrete, and for that also we can use the retarders. Now, what is the basic chemistry behind working of an accelerator? Since cement hydration, we have cations and we have anions. So we have seen calcium are cations, they carry positive charge, and silicates and aluminates, they are anions, they carry negative charge. Okay, so among these, if we talk about a cement grain, okay, so we know hydration is a surface phenomena. Once hydration happens on the surface, there is osmotic pressure buildup, and when that osmotic pressure breaks, there is dissolution of ions as water ingresses in. Okay, now among these ions, silicate ions, the rate of dissolution of silicate ions is the slowest compared to other. Okay, compared to calcium and aluminates. So what is the function of accelerator? It increases the ionic availability by introducing calcium ions, chloride ions, and nitrate ions into the system, and they reduce the energy barrier for hydration. So what they will do, they will increase the rate of dissolution of ions, and as they increase the rate of dissolution of ions, they increase the rate of hydration. Okay, so there can be a hardening accelerator which increases the rate of dissolution of calcium silicate and increase the formation of CSH at early ages. And there can be set accelerators which allow C3A to react faster by dispersing the effect of gypsum, which delays the C3 hydration. Okay, so either they can increase the rate of dissolution of calcium silicate, and which will increase the rate of formation of CSH, or they will hinder gypsum from interacting with C3A such that C3A can react with water and cause flesh setting. Okay, so in both way accelerator can work. It can increase the hardening rate also, or it can increase the setting rate also. Okay, so commonly used admixtures accelerators are calcium chlorides and sodium chlorides. However, we don't want chlorides in system also because they can cause durability issues in reinforced concretes. So that's why there are non-chloride admix accelerators also, like nitrates and nitrides of calcium and sodium. There are amines, there are carboxylic acids. These are also known to have accelerating properties for cement hydration. Now, what is the basic chemistry behind working of a retarder? So, they uh, just opposite to admixture, retarded, they slow down the hydration reaction by delaying the formation of hydration product. Okay, and this they can do by three mechanism. Either they can absorb on the cement grain particles. So, suppose this is my cement grain. What retarder will do? It will absorb on the surface of cement grain. Okay, and it will form a thin protective film on the cement grain. Now when this film is formed, the water that is available inside concrete, it won't be able to react with the cement grain. Okay, so it more water is there now for workability rather than for reaction. So it will delay the hydration reaction. Okay, then they can form calcium complex for calcium complexes. So retarder, they react with calcium ions to form complexes which reduces the Ca plus content for hydration. So what they will do with calcium ions, they will react and they will form a complex. Okay, and once my calcium ions are blocked, okay, it will block the hydration reaction. It will block the formation of CSH and other hydration products. So since these hydration products are not forming due to the formation of these complexes, my water is still available in the system, which will impart workability to concrete. And third, they delay C3 hydration. So they will delay the C3A to cause setting by enhancing the effect of gypsum in delaying the hydration of C3. So they will increase the effect of gypsum to block C3A from reacting with water, and in this way also they improve the workability of concrete. Okay, so in either of these three way it can work. Okay, so the basic thing that you need to remember here is an accelerator accelerates the hydration by intervening with the cement grains, and a retarder delays the hydration by not allowing water to react with the cement grain. Okay. Now, next is air training admixtures. So, as the name suggests, these admixtures they allow controlled quantity of some small uniformly distributed air bubble to be introduced during mixing and remain after hardening. Now, so they allow air voids to stay inside concrete. Okay, that is the main purpose of air entraining admixture. Now, why would we need such admixtures? Like we know that air voids in concrete will hamper the compression. Okay, so these admixture they are mainly used to improve the freeze thaw resistance. Okay, to prevent cracking due to water expansion in cold weather. Okay, so what happens in freeze thaw action in concrete? So there are air voids which are present inside concrete. Okay, there is water that is present inside concrete. Now at very low temperature, water freezes. Okay, and it converts into ice. Now when water converts into ice from liquid state, it converts into solid state. There is an expansion in volume by about 9%. Okay, now we know that concrete is rigid. It doesn't have, it has very limited free space inside it to accommodate any expansion. So what happens due to this volume increment, there is tiny cracking inside concrete. Okay, because of the pressure that ice has exerted on the concrete. So these cracks they form, then again when water melts, space is freed up, then again ice will form, it will again increase this cracking. Okay, so in this way it will cause cracking, scaling, and eventually structural damage to concrete due to continuous freeze and thaw cycles. Okay. So, if the concrete is not designed to handle this volume expansion, then it will be a very big structural problem in cold weathers. Okay, and to sort this problem, we have air entraining admixtures. Okay, that are introduced inside concrete. So, what these admixture do? They increase the quantity of air voids inside concrete, which can accommodate any kind of expansion that is happening. So when there is expansion, these air void will provide the space to uh, bear that pressure. Okay, the expansion volume, it will bear the expansion volume and it won't allow concrete to crack. Okay, how they function? Again, they have hydrophilic head and a hydrophobic tail, just like dispersing agents. So what these are also surfactants which are hydrophilic head and hydrophobic tail. So they reduce the surface tension of water by absorbing on the interface. So at the hydrophobic part, it surrounds the air bubble. So initially, we know during pouring of concrete, there are voids inside concrete. So these admixture, they surround the air voids and they stabilize these air voids from rupturing. Okay, so when we do compaction, we see that air voids, they come merge with each other and they rupture and they densify concrete. But when we add air entering admixtures, they don't allow air voids to interact with each other, and they allow that these air voids are there inside the system and they are not broken. So that is the purpose of the hydrophobic part. Okay, it prevents the air void from merging, while the hydrophilic end, it interacts with water and it stabilizes the system. So in this way, air voids are maintained inside concrete, and these air voids will help us to deal with the freeze thaw action that is happening in cold weather. Okay, so these viscol, resin, aliphatic hydrocarbons, lignosulfates, fatty acids, these are all one of the type of air entraining admixtures. Then there are viscosity modifying admixtures which are used in concrete to enhance the viscosity of the system. Okay, and by what do we mean by viscosity enhancement? It helps us to control segregation, bleeding, and flowability of concrete by making concrete self-compacting in nature. Okay, so you can see this image here. What we mean when we say about viscosity modifying admixture. Okay, so if you see here, I have a concrete which has initial slump like this. Okay, so at 0 second, when I place the slump cone, my concrete had this shape, and this is highly viscous concrete. Okay, first see the second part. Okay, this is a concrete without viscosity modifying admixture. Okay, so what happens at 0 minute? This has this slump like this, shape like this, and as soon as I will remove the slump cone, what will happen? The entire concrete, it will settle down. Okay, due to the action of gravity. Okay, now what viscosity modifying admixture does? It imparts viscous nature to concrete. So you can say, see that under gravity it is not collapsing as quickly as it was collapsing without the use of viscosity modifying admixture. So this is what we say viscous, this is why we say it makes concrete viscous in nature. It reduces the segregation or bleeding inside concrete by making concrete viscous in nature. Okay, so how does this admixture work? So again, they are long change of polymer molecules. Okay, and they modify the flow behavior of cement paste by increasing the cohesiveness and the viscosity of cement paste. They absorb on water. Okay, and they increase the viscosity. They are associated with each other. Okay, and they increase the viscosity, and they are interlinked to each other, and they increase the viscosity. Okay, so either by absorption on water, either by interacting with each other, and either by intervening with each other, they enhance the viscosity of concrete. Okay, so instead of acting on the cement grain, these admixture, they act on water, and they make our concrete viscous in nature, which is very important in self compacting concrete. Okay, Then there are some very, apart from these commonly used admixtures, there are few other less frequently used admixtures like shrinkage reducing admixture, which reduces shrinkage cracking. Okay. And there is waterproofing agent which are used in concrete to prevent water penetration inside. And there are alkali silica reaction mitigating admixtures which reduce the cracking due to alkali silica reaction. So these are very rarely used admixtures. So we'll just skip this part and we'll just focus on the main admixtures which are used on concrete. However, I have provided one slide where I have written the function, mechanism, and some of the commonly used admixture for all these three categories. So you can have a go on this also. Okay. Now just try to answer these three questions based on accelerator, retarder, viscosity modifiers, and one more category, iron training agents discussion that we saw. And in the meantime, if you have any doubt regarding chemical admixtures, you can ask. Retarder increase setting time, accelerator decrease setting time. So suppose you had a normal concrete which had an initial setting of 30 minutes. With the addition of accelerator, you can decrease the setting time to 15 minutes. Okay. And with the use of retarder, you may increase the setting time, initial setting, till 45 minutes. Okay. So it is retarding the setting, it is delaying the setting. That is the function of a retarder. Just try to answer these three simple questions now. Okay, so for question number one, what question says, which of the following is a common mechanism of crystalline waterproofing admixture? Okay, so the correct answer is B. Yes. So if we talk about waterproofing admixtures, there is a product which is commonly present in market which are known as crystalline admixtures. So what these crystalline admixtures do? These crystalline admixture, what they do, they penetrate inside concrete and they react with free lime, which is present inside concrete. Free lime, calcium hydroxide, which is present inside concrete, and they convert it into CaCO3. Okay. Now, once this free lime is converted into CaCO3, we know CaCO3 is a solid product. Okay. So it is a precipitate. In these precipitate, what they do, they block the pores inside concrete, and as they block the pores inside concrete, they won't allow water to penetrate deep inside concrete. Okay. So this is the working of a crystalline admixture. Okay. These admixture are gaining much attention in market. You will see a lot of crystalline admixture products which are coming up, because when we block concrete pores, it helps us to it helps us to tackle a lot of durability issues also, because water is a very common source, a very common carrier for durability issues in concrete. Question number 5. Can anyone answer? The effectiveness of shrinkage reducing admixture can be reduced when used in conjunction with. So I have a concrete where I'm using shrinkage reducing admixture. Now, which other admixture, if I add with this shrinkage reducing admixture, will hamper performance of each other? Like which two admixtures can't be used with each other? Any guesses? So we know that shrinkage reducing admixture, it will deal with shrinkage problem. Okay, the cracking due to shrinkage. Why cracking occurs due to shrinkage? When there is water which is present inside concrete, and when concrete loses water, it will shrink, and due to the shrink, it will there will be cracking inside concrete, because in hardened state my concrete has a definite volume, and any change in volume in that hardened concrete, it will cause cracking. Okay, now which admixture do you think will do a negative effect on shrinkage reducing admixture? Yes, the correct answer is C. Because in air entraining agents, when we add air entraining admixtures to concrete, we are increasing the air voids inside concrete. Now, in fresh state, these air voids are occupied by water. Okay. Now, over time, what will happen? If I am adding shrinkage reducing admixtures also, it will reduce the ability of concrete to create these air voids. Okay, and in this way, both shrinkage reducing admixtures and air entraining admixture, they will compromise each other's working ability, and they will compromise each other's effectiveness. Now, third question: which admixture is sensitive to temperature variation? Okay, so you know the mechanism of all these admixtures. Which do you, can you tell me which admixture will be sensitive to temperature? So we know that at high temperature it increases the rate of reaction. Lower temperature decreases the rate of reaction. So which admixture will be affected by this temperature variation effect? Yes, the correct answer is D, accelerator. Why? Because accelerating admixture are the primary function to speed up the setting and the hardening of concrete. Now, in high temperature, what will happen? This 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 high temperature will promote accelerating admixtures, because in high temperature reaction kinetics is already very fast. So accelerators which will work effectively. However, in low weather, low temperatures where reaction kinetics is slow, my accelerator may not work that efficiently. Okay, so that's why accelerators and retarders both, they are sensitive to temperatures, because temperature itself can cause variation in rate of hydration. Okay, and that can affect the effectiveness of accelerators and retarders, which also interact with cement hydration. Okay, any doubt in the entire discussion of chemical admixtures? Any admixture that you have doubt, you can ask. So this was something which was left from week 3 live session that we were not able to complete in last session. So that's why it started it here, and now we'll move to the week 4 content that was loaded on the SOIAM portal. So any doubt in the admixture part, chemical admixture? Air in training admixture. Okay, so let's see that thing at the end. If you want me to complete repeat that part completely, we'll talk it at the end. Okay, just drop a reminder again. If you have any small doubts, if you have regarding any question that we discussed, or any very small doubt that I can clear in a minute or so. So if you, any one of you, if you have any doubt, you can just keep it posted in the chat box. At the end, we'll look at it again. Okay. Now, after chemical admixtures, we have mineral admixtures. So, what are mineral admixtures? So, if we go along the basic definition of admixtures that is given by IS 9103 guideline. So, this guideline says that an admixture is a material other than water, aggregate, and cement which are used as an ingredient for concrete or mortar and added to batch immediately before or during mixing to modify one or more properties of concrete in plastic state or hardened state. So this is the definition that is given in code for admixtures. Now, we know that admixtures are further classified in two types, mineral admixtures and chemical admixture. And as we have already talked about chemical admixture, it satisfies this definition. How? As it is added in concrete during mixing and it modifies one or more properties of concrete in the plastic state. Okay. Now, what are mineral admixtures? So these are finely divided siliceous material or powdered material which are added in concrete to improve the properties of concrete in hardened state. Okay. So they are also known as supplementary cementitious material because they are added as a partial replacement of cement. Okay, for enhancing the performance of concrete. So we saw admixtures, they were added also as a partial replacement of water or cement, and here supplementary cementitious material, they are added as a partial replacement for cement. Okay. And what are the benefits of using these mineral admixture, or we can say SCMs? Okay, they promote sustainability by reducing cost and energy requirement as they are replacing OPC. Now, how they promote sustainability? Because we are using them as a partial replacement of cement, and we know that cement is expensive is an expensive material. It requires a lot of energy and it generates a lot of CO2 during production of cement. So instead of cement, when we use an SCM, which are basically generated from waste residue material, they are reducing both cost and energy, and they are helping us to build sustainable construction practices. And second, they improve strength and durability of concrete by either by reducing the water demand for concrete, by improving the rheological behavior of concrete, by making concrete less permeable and denser, or by acting as a filler. So, by any of these means, they improve the strength and the durability of concrete. Now, how these supplementary cementitious materials are produced. So, a couple of weeks ago, we had a very brief overview of source of production of few SCMs. So, today, let's see these things in a little bit detail. So, most commonly used SCMs are fly ash, ground granulated blast furnace slag, and silica fume. So, our discussion for today will focus on these three SCMs only. So, first is the production of fly ash. So basically, fly ash is a fine particulate residue which is an outcome of coal burning obtained from coal-based electric generation plant. Okay, they are also known as pulverized fly ash. So these are residue product of coal burning, we can say. Okay, now how they are produced? So first, coal is pulverized. Okay, by what do you mean by pulverization? It means coal is grounded or hammered into fine powder. Okay, and this pulverized coal, they are burnt in boiler to produce heat that is used for generating electricity. Okay, so we know from coal we generate electricity, so that is the process that is happening here. Okay, now during combustion of coal, the inorganic particles that are present, inorganic minerals that are present in coal, like silica, alumina, iron, and calcium, they do not burn completely and instead they convert into molten ash. Okay, so instead of burning completely, they convert into ash. Okay, and which are very lightweight in nature. So this ash that is produced inside this burner, they are very lightweight in nature. So these ash, they are carried upward with gases. Okay, hot flue gases inside the burner, and as these gases moves away from the high temperature zone, the ash also moves away from high temperature zone and they cool down. Okay, and once they cool down, they solidify into fine glassy powder material which is known as fly ash. Okay, so you can see gases, they flew away, they are brought to precipitators. Okay, and here they are cooled down and they convert into powdery material which is known as fly ash. So the powdery material that is formed, it is separated from flue gases by the help of precipitators. Okay, which are like electrostatic precipitators or baghouse filters, and from the separation we get the powdery material which is fly ash. Okay, and this fly ash that is produced from coal burning, they are either used in construction activities as a replacement of cement, or they are deposited in ash pond or landfills if not reused. Okay, so what type of fly ash we are producing, the quality of fly ash, it completely depends upon the quality of coal. Okay, so there are two types of fly ash. There is class F and there is class C. Okay, so class F fly ash is derived from burning of bituminous or anthracite coal. Okay, and it has low calcium content in it. And class C fly ash is produced by burning of subbituminous coal or lignite coal. Okay, and they have very high calcium content in them. Okay, so the source of burning, it dictates the composition of fly ash that is produced at the end. Okay, so this is how fly ash is produced. Okay, it is a waste residue from coal burning. Now, after fly ash, we have ground granulated blast furnace slag. So they are obtained by quenching molten iron slag, which is a byproduct in steel making industry from blast furnace in water and steam. Okay, so in simple term, we can say it is a byproduct of steel making process, especially from the production of iron in the blast furnace. So during production of iron in blast furnace, we have iron ore, we have coke, which is a source of calcium, which is carbon rich material, and we have limestone, which is fed in a blast furnace. Now here coke act as a fuel and a reducing agent, while limestone helps us to improve remove purity. So at high temperature of around 1500 degrees Celsius, when we burn iron ore, coke and limestone, what happens, iron ore, it is reduced into molten iron. Okay, and the impurities that are present in the iron forms a molten slag. Okay, which floats at the top of the molten iron. Okay, so what we do, we separate the slag, molten slag, from molten iron, and to produce granulated blast furnace slag, this molten slag is rapidly cooled by quenching in high pressure water, and this rapid cooling, which is known as granulation of slag, it prevents gives this slag glassy structure. Okay, once we get this glassy granulated slag, it is grinded, and after grinding we get ground granulated blast furnace slag, which is amorphous and reactive in nature. Okay, so again, what is a ground granulated blast furnace slag? Is it a residue of iron making industry? So the slag, molten slag, which contains all the impurities in iron ore, it is separated from melted iron, and it is granulated and grind to produce a white powdery material, which is ground granulated blast furnace slag. And next we have production of silica fume. So primary raw material is silica. Okay, here, so silica fume, it is a byproduct of ferrosilicon alloy or silicon metal, which is produced in electric furnace. Okay, so silica quartz, it is combined with carbon source like coal, coke and wooden chips. Okay, and these materials, they are heated in an electric arc furnace to produce silica or ferrosilicon alloys. Okay, so inside these furnace there is temperature of around 2000 degrees Celsius. Okay, at this high temperature, what happens, there is a reaction that is occurring. The silica, it reacts with carbon to form silica atom, and it releases carbon monoxide. Okay, so the silicon metal, it is collected at the bottom of the furnace, and this uh, carbon monoxide or silica oxide, monoxide, these gases, they raise at the top of the furnace, where they are separated from the silica, and they are combined with oxygen in the cooling chamber to form SiO2 again. Okay, so this CO and SiO residue, which is formed during heating, it is separated from the furnace, it interacts with oxygen in the cooling chamber, and it again forms SiO2. Okay, so this is SiO2 which is formed, it is known as silica fume. These are fine powders of the silica fume, okay, and they are filtered from other impurities using backhouse dust collectors and purifiers, and they are densified or left in their original form to get silica fume. Okay, so there can be densified silica fume, there can be powdered silica fume, and there can be a slurry form of silica fume also where it is mixed with water. Okay, so this is again, we can say, a residue of a silicon metal forming industry. Okay, this silica fume, and it is also amorphous in nature. Okay, so this is how all three very commonly used admixtures are produced: fly ash, slag, and silica fume. All are a byproduct of other industrial product. Okay, and if they are not used, they will be dumped. So instead of dumping, we have researchers have found a way to reuse them as a replacement of cement, so that they can be consumed in instead of getting dumped. Any doubts here? No. Now comes the important part. These produced SCMs, they are all amorphous in nature, and these amorphousness was imparted in these SCMs either due to rapid cooling or due to grinding of the SCMs. Now, these SCMs, although they are amorphous in nature, they don't react with water on their own. So it is not like the SCMs that we are adding. It is not like these SCMs, when I add water, they will show form hydration product. No, they are not able to react with water directly. Although they are amorphous in nature, they don't react with water directly. Okay, but if we have OPC also present in the system, then SCMs, they react to form hydration product. So this nature of SCMs is known as pozzolon. Okay, and they refer to class of siliceous and aluminous material which on their own they don't have any cementitious property. However, in a finely divided nature and in the presence of moisture and cement, they react chemically with calcium hydroxide released during the hydration of Portland cement to form cementitious properties. So what happens when OPC, it reacts with water, it forms CSH and CH. And we know that CH is not desirable to us. So what SCMs do, they are amorphous in nature due to the presence of amorphous silica and alumina. And this amorphous silica and alumina, it combines with the produced calcium hydroxide during OPC hydration to form calcium silicate hydrates or calcium alumina hydrates. Okay, and in this way, these SCMs, they are used during hydration, and this reaction, secondary chemical reaction between silica from pozzolon and lime from cement, it is known as pozzolanic reaction. So silica from pozzolana, it is reacting with calcium hydroxide from cement hydration in the presence of water to form calcium silicate hydrates, and this reaction is known as pozzolanic reaction. And that's why they have an ability to replace certain part of OPC by showing this reaction, pozzolanic reaction. Okay, because they are able to form CSH from the waste generated by OPC. So suppose if I wanted 100 grams of CSH to be produced, so the by if I am able to use the waste that OPC is producing to create make CSH, then I can reduce the content of OPC required and I can replace it with SCMs. Okay, so that's why they are used as a supplement to OPC for enhancing the strength and the durability of concrete. Okay, so there is CSH and there is alumina containing pozzolon. They react to form calcium aluminum hydrates. Okay, which can also contribute to strength of concrete. Okay, so this is the action of SCM. They are not directly reacting with water, but in the presence of a calcium hydroxide source, they can react to form cementitious properties. And this reaction is known as pozzolanic reaction. Now, based on the understanding about properties of production of SCM and how pozzolanic reaction, just try to answer these five questions. And in the meantime, if you have any doubt regarding this discussion of mineral admixtures, you can ask. Yes, one of you raised hand. What is your doubt? If you are not able to unmute, you can type in the chat box. Others who don't have any doubt, just try to answer these questions. There are 5 questions on this slide. Just think about the discussion that we had about mineral admixture till now and try to answer these questions. First question is, what is the primary environmental benefit of using mineral admixture like pozzolans in concrete? Yes, the correct answer is B. It reduces CO2 emission by replacing Portland cement. So this is, you know why this is happening, okay, now already, because during cement production, we require a lot of fuel for creating high temperature inside furnace, and during burning this CO2 released due to combustion of limestone. Okay, so if we are using SCMs as a replacement of OPC, we are reducing the demand for OPC, and eventually we are reducing the CO2 emission caused by OPC production. Yes, Karthik, if you have doubt, you can ask. Either you can unmute or speak, or you can type in the chat box. Others try to answer question number 8. Which of the following statement about pozzolanic reaction is false? So there are 4 statements that are given here. Which one is incorrect? No, statement A is correct. We saw pozzolanic reaction where it consumes the leftover calcium hydroxide and react with calcium hydroxide to form CSH. So this statement is correct. It reduces calcium hydroxide content in concrete because it is getting consumed. The correct answer will be C. It increases the permeability of concrete. So when we add SCMs, we are consuming calcium hydroxide, and we are converting this, which usually used to be a waste, to concrete hydration, cement hydration. We are consuming that waste and we are forming calcium silica hydrate. So when we form calcium silica hydrate, we are densifying the concrete. Okay, calcium hydroxide was precipitate product which was present in the pore spaces in concrete, and that product now it is getting consumed into a solid precipitate. Okay, so we are densifying the concrete, and when we densify the concrete, we are reducing the permeability of concrete, and we are not increasing the permeability of concrete. So this statement is false. Question number 9. Which statement best describes the role of alumina in pozzolanic materials? So we saw one line in the last slide. If you remember that line, can anyone tell me what will be the correct answer? The correct answer will be B. So what happens in pozzolanic reaction? Amorphous alumina also reacts with calcium hydroxide to form calcium aluminate hydrate, which can also contribute to synth and sulfate resistance properties. Okay, so everything is related to enhancing the strength and durability of concrete when we talk about addition of SCMs to concrete. Question number 10. Silica fume is a natural pozzolan. Whether the statement is true or false, can anyone tell me? Is silica fume is a natural pozzolan or an artificial pozzolan? How it is true? Actually, silica fume is not a natural pozzolan. It is an artificial pozzolan. Why it is an artificial pozzolan? Because we are producing it as an because it is produced as a byproduct of an industrial from an industry. So it is a byproduct of the production of silicon metal or ferrosilicon alloys in electric arc furnace. Natural pozzolans are those material which are naturally occurring, like volcanic ash, pumice, diatomaceous earth material. They all have amorphous silica and alumina in their composition naturally, which makes them possess pozzolanic properties. Artificial pozzolans like silica fume, fly ash, and blast furnace slag, they are industrial byproducts that exhibit pozzolanic behavior due to their production, due to the rapid cooling, due to grinding. They are imparted pozzolanic properties, and that's why they are artificial pozzolans and not natural pozzolans. Question number 11. The pozzolanic reaction occurs immediately after mixing with concrete. Whether the statement is true or false. Whether pozzolanic reaction is an immediate reaction or a long term reaction. Can anyone tell me what will be the answer? True or false? Why false? Can one of you tell me? Why it is not an immediate reaction?
Basically, Pozzolanic reaction is a slow and start after the hydration of cement, not
Yeah.
immediately.
But hydration of cement starts as soon as we add water in cement.
Sorry, sir. Can you repeat the question?
We know that hydration reaction starts as soon as we add water in cement. So then why this is a slow reaction, not a fast reaction?
It continues over a long time and improves long-term strength.
Huh, but won't why it is like the question is whether it occurs immediately or after a long time. So you are saying it improves the long term strength, but whether it will occur immediately or at later ages, and why not immediately? See, the correct explanation why it is a slow reaction is because it requires calcium hydroxide to be produced, then only SCMs can react. Okay, so when we talk about hydration of cement particles, we have seen that initially C3A reacts and then slowly C3S and C2S reacts. When C3S and C2S reacts, they produce CSH and CH. And only when CH is produced, then only SCMs can come into picture, not before that. So that's why it is not it this reaction doesn't occur immediately after mixing with concrete. Only when CH is produced, then HCMs will start reacting. So that's why they are slow uh, secondary reactions. Okay, I hope it is clear. Your answer was correct, but explanation should be according to this because it requires CH to be produced for reaction. Now, before moving into how these mineral admixture are actually affecting the concrete properties, like we did in the first live session with Portland cement, it is important for us to understand why these mineral admixtures are reactive, how they react, and how they differ from one another. So, if we are able to answer these three questions, we can build a generalized knowledge that we can use for any other mineral admixture. Okay. Now, the second question we have already discussed how they react. It is due to pozzolanic reaction. For the other two, like why they are reactive and how they differ from each other, we need answers. So first we'll look at the characterization of SCMs, in which we have scanning electron microscopic image of these pozzolanic materials. So you can see this is for fly ash, these two image. This image is for ground granulated blast furnace slag, and this image is for silica fume. Okay, this is at a magnification of 200 micron. This is at a magnification of 2 micron, and this is at a magnification of 500 nanometer. Okay, very small scale. It is zero point 0.5 micron. Okay, so how they are able to differ from each other at this? So you can see fly ash particles, they are spherical in nature, and they exist in two forms: cenosphere and plerosphere. Okay, so in cenospheres, these are hollow lightweight spheres that you see here. These are hollow spheres, and they are useful in lightweight construction materials, like for you making lightweight aggregates through pelletization or sintering process. And this palospheres, they are large spheres which contain small fly ash particles within them. Okay, so in general, we say fly ash are spherical nature. These are spherical in size. Fly ash particles are spherical in size. Then we have GGBFS. So unlike fly ash, which is spherical, GGBFS particles are angular and irregular, and this is due to rapid cooling of molten slag followed by grinding operation, which makes these spherical particle turn into angular and irregular particle. So we saw in fly ash, we are not doing grinding, we are just doing rapid cooling. In silica fume also, we are just doing rapid cooling. But for ground granulated blast furnace slag, after granulation there is grinding also which is done, and that grinding, it disturbs the shape of the particles, and it makes them angular and irregular in nature. Okay, so this is how ground granulated blast furnace slag looks under a microscope. Now next is silica fume. So, unlike slag and more like fly ash, silica fume particles are spherical in nature. However, they are ultra fine and nearly spherical particles, and almost 100 times smaller than cement grains. Okay, now this you can understand from the difference in the difference in the size of a silica fume and fly ash. You can see based on the scale of SCM image. So if you see fly ash, here the scale was 200 micrometer. However, for silica fume, the scale is 500 nanometer, which is equivalent to 5.5 micrometer. So these are very small, tiny particles, spherical particles. It is like almost 10 to 15 times smaller than the size of a fly ash particles. And since they are very small, they are very fine particles, they have very high surface area, and that's why silica fume is very highly amorphous in nature. Okay, so from basic structure of these SCMs, we can have an idea about how these SCMs, they will contribute in hydration reaction. Now, the effect of particle microstructure and particle size can be seen in terms of quantitative entities like specific gravity and fineness, as you can see in this table. So, OPC, it has a fineness of 300 to 400 meter square per kg. Class C and Class F fly ash also belong in the same range. Ground granulated blast furnace slag also belong in the same range. However, silica fume, it is much finer than these other cementitious material. It has a fineness of more than 10 to 15 times finer than OPC, fly ash, and silica fume, yeah, and GGBFS. So that's why it is very highly amorphous in nature. And in terms of specific gravity, all these SCMs, they are lower specific gravity compared to OPC. So these are lightweight ash materials. Okay, that's why they have lower specific gravity compared to OPC. So higher fineness typically means faster reaction and increased surface area for hydration. Since silica film is ultra fine, approximately 100 times smaller than OPC, it contributes to highly amorphous nature of silica film. Fly ash particle tends to have low specific gravity due to their hollow spherical nature, as we saw in the microstructure, while GGBFS has low specific gravity closer to OPC, although lower but still very closer to OPC because of its dense glassy structure. And finally, in characterization comes chemical composition. So if you just focus on major composition, silica oxide, alumina oxide, and iron oxide and calcium oxides, you can see compared to OPC, GGBFS higher proportion of silica oxide and calcium oxide. Now, since along with SiO2, there is a higher proportion of Ca also in GGBFS, it is observed that GGBFS show latent hydraulic reaction. Hydraulic reaction. What do you mean by latent hydraulic reaction? It means that it can act as a pozzolon also, where it waits for CH to be produced for reaction, or it can show self-cementitious ability also under some given circumstances. Okay, so it doesn't always require cement to react with water. It can by itself also it can react with water because it has calcium oxides in it in its composition. Then we have class F fly ash, where you can see there's higher proportion of silica and alumina in its composition, and very low proportion of calcium oxide. And class C fly ash has higher proportion of alumina, silica, and calcium oxide. Compared to class F, lower content of silica but higher content of CO. And again, since it has qua- sufficient quantity of calcium oxide, it can also show self-cementitious ability. And then there is silica fume, which has very high content of silica. So it is 90, more than 90%, and usually in the range of 97 to 97%. Okay, reactive silica is there in silica fume, which makes silica fume a very strong pozzolanic material. Now we have answered two questions: how mineral admixtures are reactive and how they differ from one another. But how to judge or find the reactivity of a mineral admixture? Like before actually using it for field application, how we know how much reactive a mineral admixture is? So for this we have two testing. First is pozzolanic activity index testing. So this testing measures the ability of a pozzolanic material to react with calcium hydroxide in the presence of water, and this testing is done in as per ASTM C618 guideline. Okay, and this was used for fly ash. This testing was initially built to test fly ash. So what we do, we prepare a mixture of OPC and pozzolanic material, usually by replacing 20 to 30% of OPC with pozzolon, that is fly ash suppose, and we prepare samples, mortar samples, and cure it in concrete standard condition for 7 days and 28 days. Now after 7 days and 28 days, we test these cement mortar samples for compressive strength, and we check the ratio of compressive strength with blended cement, where there is both fly ash and cement, and we check the compressive strength for pure cement, pure OPC, and based on the increment we determine the pozzolanic activity index. So if my PAI value is 75% or higher, it indicates that the pozzolanic material has good pozzolanic activity according to STM standard. Okay, so suppose without using SCM, I was getting a strength of 20 MPa, and with using SCMs, I am getting a strength of 35 MPa. So, what is my increment? 15 MP increment. So, my total increment will be 15 upon 20, uh, 35 upon 20 divided by 100. Okay, so this will be my PIA value, PAI value. Okay, so it will define how much increment I have got in strength compared to control. Then there's lime reactivity test, which measures the rate of at which pozzolanic materials they consume calcium hydroxide. Okay, and this test is done in as per ASTM C 1311 and IS 17227 guideline. So in this testing, what we do, we take lime, which is CH. Instead of waiting for OPC to produce lime and then making it react with SCM, what we do in this testing, we directly take pure lime, CH, okay, and we add pozzolanic material in it and a quantity of weight quantity of water, like 1 is to 2 is to 9 ratio. So 1 will be my SCM, 2 parts will be my CH, and 9 parts will be my water. Okay, we make this mixture and we let it set in controlled temperature and humidity condition, and after curing we determine how much CH is consumed. Okay, so suppose initially there was 10 grams of CH and 20 grams of SCM, or we can say 10 gram of SCM was there and 20 grams of CH was there. Okay, now I have prepared paste using this two plus water. Okay, and after 7 days I will powder this paste sample and I will check how much CH is remaining. Okay, so what will happen? SCM, it will react with CH to form CSH. Okay, but there will be still some CH left which is unreacted. So I will try to quantify the unreacted CH either using titration method or thermal analysis, and from that I will calculate the percentage of lime consumed by the pozzolon. So higher lime consumption indicates that there is so strong pozzolanic activity, and from this we can get an insight of long-term performance of a pozzolon. Okay, so these were two testing for assessing the pozzolanic activity. Now just try to answer these four questions based on characterization of SCMs and testing of SCM. And in the meantime, if you have any doubt, you can ask. Think about question number 12 and answer uh, what will be the correct sequence of reactivity. Can anyone tell me the answer for question number 12? What is the sequence of reactivity of fly ash, slag, and silica fume in early stages of hydration? Which one will be the most reactive and which one will be the least reactive? Okay, so the correct answer will be B for this. Silica fume is the most reactive because it is 97 to 98% amorphous silica. It is there in its composition and it is very fine in nature. So that's why it is the most reactive. Now between slag and fly ash, we know GGPFS shows self-cementitious properties also due to its latent hydraulic nature. So initially, even if there is no CH present in the system, due to the presence of alkali ions inside the pore matrix, GGPFS can show some cementitious properties. So that's why it has higher strength compared to a class F fly ash, which has very little CO, and it strongly depends upon CH for reaction. So this is the correct order for reactivity. The lime reactivity of class A fly ash is typically lower than class C fly ash. Why? So I have a batch of class F fly ash and I have a batch of class C fly ash, and I did lime reactivity testing for it. So it was found that class F fly ash was consuming less lime compared to class C fly ash. Why is that so? Can anyone tell me the answer for question number 13? The correct answer for this will be C, because class F fly ash has low calcium content and high silica content. So it requires external activators like lime to show reactivity. However, in class C fly ash, there is high calcium content. So this makes it more reactive towards lime and water. Okay, this is the basic reason is the composition. Okay, presence of lime in class C fly ash makes it reactive, more reactive than a class F fly ash. Question number 14. GGBFS can act as both a latent hydraulic material and as a pozzolan depending upon its chemical environment and curing condition. Whether the statement is true or false, can anyone tell me? Yes, this statement is true. So we have already discussed GGBFS act as a latent hydraulic material in the presence of water and certain activators like alkali ions, and they behave as a pozzolana also when combined with Portland cement. As Portland cement release calcium hydroxide, it can react with calcium hydroxide to form calcium silica hydrates. So the correct answer for this is true. Question number 15. Which of the following factors least affect the pozzolanic reactivity of GGBFS? Can anyone tell me? What will be the correct answer? Okay, correct answer will be D. I am quickly moving to these through these questions because we have a lot of discussion pending and we have very little time. That's why. So glassy nature, if GGBF has higher glassy phase, then it will increase the reactivity. Fineness will increase the reactivity. Calcium content can alter the reactivity and strength gain. However, ambient carbon dioxide concentration, it is not related to the strength or activity of GGBFS. So that's the correct answer is D. Now, answer these two questions also. In SCM imaging, the smooth spherical particle observed in fly ash samples are indicative of what? Why there is smooth spherical particles in fly ash? What is the reason behind getting a smooth spherical particle? Can anyone tell me why fly ash has smooth spherical particle but slag doesn't has spherical particle? What is the reason? The correct answer will be A, due to rapid cooling. So we saw that there are two things that we are doing with the residue that we have collected. Either it is rapid cooling or it is grinding. So when we do rapid cooling, we give a smooth spherical shape to the residue. However, when we do grinding followed by rapid cooling, we impart angular and uh, heterogeneous irregular structure to the fly to the ash, and that is what we observe in ground granulated blast furnace slag. However, in fly ash we are just doing rapid cooling, which imparts the spherical nature. Now, in SCM image, what will be the feature that will indicate incomplete combustion of fly ash? So just by seeing the SCM image, how you can judge that there is incomplete combustion in fly ash? Can you tell me? So this might be a little difficult question to think about. So I will tell you the answer. It will be the irregular angular particles. Okay. So we know that fly ash, they are smooth and spherical in nature. But if we are observing irregular angular particles under SCM, we can say that there is presence of unburned carbon residues, and these unburned carbon residues, if they are present, they have irregular shape. These are porous and irregular in nature. So a properly combusted fly ash, it will have very smooth glassy spherical particles, and an improperly combusted fly ash will have irregular porous particles of unburned carbon also in its and in its SCM image. Okay, so this is how an SCM image can also be very important to understand the characteristics of a material. Okay, so let's move ahead to the next segment. Now we have this next we have is hydration reaction of pozzolanic. So as we have seen earlier also, pozzolanic reaction is where reactive silicates and aluminates in pozzolan, it reacts with lime to produce hydration product. So the same thing I have again repeated here in the two equation. So CH is coming from OPC, it reacts with reactive silica and alumina present in SCMs in the presence of water to form calcium silica hydrates and calcium aluminate hydrates. Now, what are the benefits of these reaction? It is consuming lime, which is promoting durability. It is refining pores. It is producing, promoting durability. It is enhancing the interface between aggregate and cement, which is increasing the strength and durability. It is a slow rate of reaction. Okay, this reaction occurs at a slow rate, so they have low heat of hydration, and they can be accelerated by alkalis and gypsums in case of slag and class F fly ash. Okay, so slag and class C fly ash, they can show self cementitious ability if alkalis are present. Okay, so that's why we say that the reaction can be accelerated by alkalis. Now, what is the effect of these SCMs on fresh properties of concrete? So here I have clubbed all three SCMs, fly ash, slag and silica fume, so that we can have a comparative understanding. So in fresh properties, first we have setting time. So fly ash, they tend to increase the setting time. Okay, they delay both initial setting and final setting. Why? Because fly ash is slow pozzolanic reactivity compared to Portland cement. So they react slowly with calcium hydroxide, which delays the hydration. And since they are delaying the hydration, they are delaying the setting of concrete. Similarly, ground granulated blast furnace slag, we say it can either increase or decrease the setting time depending upon the mix and temperature. Why? Because it has latent hydraulic property, meaning that it can react in the presence of an activator like Portland cement, and in colder condition it tends to slow down the setting, but in warmer condition it may not significantly delay setting because it is latent hydraulic in nature. It can react on its own and in the presence of Portland cement both. Okay, so that's why it may increase or decrease. And silica fume, it will reduce the setting time. Why? Because it is extremely fine particle and it has very high surface area. And if since it has very high surface area and it is extremely fine particle, it promotes hydration on its surface. It accelerates the hydration process. So what happens? The silica fume, they have very high surface area, and they provide surface for water hydration reaction to occur. And due to this, they accelerate the hydration reaction. So they will accelerate the leaching of calcium hydroxide from OPC, and they will accelerate the formation of CSH on their surface. Okay, so that's why we say that it reduces setting time. While fly ash, it increases setting time. So the key contributor here is the reactivity of the material and the fineness of the material also. Then we have effect of SCMs on water and SP demand. Okay, superplasticizer demand. So fly ash, they tend to decrease the water and SP demand. Why? Because it is spherical and smooth in nature. So these spherical particle, they tend to show ball bearing effect, which improves the workability and flowability of concrete. Okay, so this point is very important. Fly ash, it reduces the water demand due to spherical nature of its particle, which tends to slip easily along its surface, and it provides the cement paste higher workability, improves the workability of cement paste, and this is known as ball bearing effect. Okay, while ground granulated blast furnace said it can slightly decrease or may cause no significant change in water and SP demand because of its angular and finer nature than cement. Okay, which can improve the packing and reduce water demand slightly. However, this effect is not as pronounced as fly ash. And silica fume, it increases the water and SP demand. Why? Because of high surface area of silica fume, which increases the water needed to wet all the particles, and thus it increases the SP demand for maintaining workability. Okay, so this is the difference between these SCMs based on for fresh properties like setting time, water demand, and SP demand. Now try to answer these three simple questions based on effect of SCMs on fresh properties. Okay, so you just need to remember 2 points: the shape of the SCM and the fineness of the SCMs. And both these things, they dictate the effect of SCM on fresh properties: shape and the fineness. So, what will be the answer for question number 18? In concrete containing fly ash and slag, which fresh property is most likely to be affected without admixture adjustment? Yes, the correct answer is C. So we have seen both fly ash and slag, they can delay the setting of concrete as they react slowly compared to Portland cement. So they can reduce the rate of hydration and they can delay the initial setting of concrete. Question number 9. In high performance concrete containing fly ash and silica fume, which of the following is the most likely which of the following is the most likely to affect the workability within the first 30 minutes? So which properties of this combined system will affect the workability, slump loss within first 30 minutes? Okay, the correct answer for this will be B, because it has silica fume also in its mix, and silica fume we know has higher fineness, and it increases the water absorption. So in first 30 minutes you will see that silica fume particle, it will contribute to accelerated water absorption, and it will cause flocculation. Okay, because of hydration, early hydration, and due to this you will see workability loss will be happening within first 30 minutes. Okay, the initial setting time will reduce, although there is fly ash in the system, but fly ash won't come into picture until CH is produced. And silica fume, since it is highly amorphous in nature, it will initially disrupt the hydration rate. In cold weather concreting, the use of Class C fly ash is more advantageous than Class F fly ash. Why? So in cold concreting, 1% a person should prefer Class C fly ash rather than Class F fly ash. Why? Can you tell me the answer quickly? Any guesses? What is the key difference between a class C and a class F fly ash? Think about it and then think about the answer. Okay, the correct answer will be B. So we know class C fly ash has high proportion of calcium oxide in its composition, which makes it act as a self-cementitious material. Okay, and in cold weather concreting, where there's low temperature and already the kinetics of cement hydration is slow, we need certain material which can contribute to early strength gain. So that's why class C fly ash is more advantageous than class F fly ash, because class C can show at least some cementitious property, while class F will totally depend upon OPC hydration to show cementitious property. Okay, so class C it accelerates the early hydration and strength gain, which can't be done by class F fly ash. Okay, so this was the effect of SCMs on fresh properties. So we understood the effect of SCMs, we understood the characterization of SCMs first, and then we talked about what is the effect of mineral admixtures on fresh properties. Now, final part is what is the effect of mineral admixtures on hardened properties. So mainly here we'll talk about compressive strength, because all other properties like tensile strength and modulus of elasticity, they are directly influenced by the compressive strength. So in this slide, in the first figure, you can see the strength development of OPC and the OPC plus fly ash system with time. So at early ages, you can see fly ash added concrete shows slower strength gain. However, at 28 days, strength is almost similar, and beyond 28 days, it has higher strength compared to OPC. So, like in OPC concrete, beyond 28 days, strength gain is not much, but in based concrete, there's still significant strength gain occurring after 28 days also, and this is due to secondary hydration reaction. So why this change in nature is happening? Because initially fly ash is not contributing to reaction, and since we have replaced fly ash OPC with fly ash, we have decreased the OPC content also. So initially there is less OPC in the system here in fly ash added concrete, so that's why strength gain is lower compared to plain OPC concrete. However, over time, as OPC produces CH, fly ash is able to react with CH and forms CSH. So it gains strength slowly over time. And after 20 days, once entire OPC is reacted and produce CH, fly ash will continue to consume CH and produce CSH. So that's why there is delayed strength gain happening in OPC plus fly ash system. And the same thing you can understand from the second figure. So up till 20 days, the calcium hydroxide content in B. So A is this is B and this is A. Okay. So a calcium hydroxide content, sorry, this is B, and OPC plus fly system is A. So you can see there is higher calcium hydroxide content in lower calcium hydroxide content in A compared to B. Why? Because here, calcium hydroxide is getting continuously consumed as it is produced. So, after 28 days in pure OPC system, calcium hydroxide reaches its saturation limit and it is there in the system. It is not getting consumed. However, in OPC plus fly ash system, this calcium hydroxide it is continuously getting consumed and its volume is decreasing as fly ash is reacting with it. Okay, and this leads to secondary strength gain in a mineral admixture added systems. So this is the effect of mineral admixture on compressor strength. Now, after mechanical properties, we have durability properties where we will first talk about shrinkage and creep. So, we know that drying shrinkage refers to reduction in volume in hardened concrete due to loss in moisture. And fly ash and slag, they reduce the drying shrinkage by making concrete denser and less permeable. However, silica fume increases drying shrinkage. Why? Because of autogeneous shrinkage, shrinkage due to internal chemical reaction. Silica fume reacts very rapidly with concrete, and due to this rapid reaction there is heat generation inside concrete, and that heat generation can lead to uh, evaporation of moisture, which can lead to shrinkage issues in concrete. So that's why it is said that silica fume based concrete needs proper curing. However, fly ash and slag, they reduce drying shrinkage issues. Why? Because they are making denser microstructure and lower permeable concrete, and their rate of reaction is also slower. So the issue of drying shrinkage is not much in these concrete. And creep, so creep is time dependent deformation of concrete under sustained loading. Okay, even after removal of load, concrete continues to deform slowly over time. Okay, and that property is known as creep. So creep behavior in fly ash and silica fume are similar. They are higher at early ages, but they reduce over time due to improved microstructure and strength gain of concrete. So what happens in creep? We have a concrete column and it is continuously subjected to a load P, which is lower than the ultimate load of concrete. And due to this continuous load over concrete, it will undergo certain deflection over time. And this deflection is known as creep effect. Now, in GGBFN's fly ash added concrete, initial strength of concrete is lower, so this creep effect can be higher. However, over time, as these concrete they gain strength, they will reduce the creep effect in concrete, and that is what was written in this point. And silica fume, they generally reduce creep at the start also because of high early strength gain in concrete, which makes concrete very stiff and which reduces the uh, this deflection in concrete from early ages itself. Okay, so this is the effect of SCMs on drying shrinkage and creep. Then we have its the effect of SCMs on corrosion rate and reinforced concrete. So this topic we'll talk later also in durability of concrete, but for now, just remember this. Now, this system of reinforced concrete was earlier supposed to be inevitable. We said that reinforced concrete is very compatible in nature. Concrete has brittle properties, steel has tensile property, and they both complement each other and they have infinitely long lifespan. However, in aggressive environmental condition, reinforced concrete can degrade, which can raise issues of durability concerns. And major durability concerns in reinforced concrete comes due to corrosion of embedded steel reinforcement. How this happens? When chlorides and carbonates from environment they penetrate through concrete and they reach the steel reinforcement surface here, they can break the passive layer which is present over the steel reinforcement and corrode the steel reinforcement. Once this steel reinforcement is corroded, its effective cross sectional area decreases, and thus the tensile strength of concrete reduces and it causes durability issues to concrete. Okay, so chlorides, what SCMs does, it makes concrete less permeable. It refines the pore structure, so it reduces the permeability of these chloride ions through concrete. It can reduce the diffusion rate of chloride ions to concrete by making concrete less permeable. It can delay the corrosion initiation, the time after which corrosion is initiating on this interface. And it can lower the electrical conductivity of concrete also by consuming lime which is present in the pore solution. So that's why we say that when we add SCMs to a concrete system, we slow the chloride increase and we increase the service life of concrete. Similarly, for carbonation, effect of SCM is mixed. Okay, so what happens? CO2, it is not causing any disruption of passive fill. However, it consumes CaOH voltage which is present in the pore solution and it forms CaCO3. Now, SCM addition has mixed effect on this. What happens when this CaOH voltage is consumed? The pH of concrete decreases. Okay, once the pH of concrete decreases, the stable passive layer which is there over the steel surface, it breaks down. Okay, now why we say SCMs has mixed effect? Because SCMs consume calcium hydroxide. So although they are making concrete less permeable, they are also lowering the CaOH content, which reduces the passive layer thickness on the reinforcement surface. So there is like two things which are happening against each other. There is denser microstructure which is lowering the rate of CO2 ingress through concrete, and there is lower pH buffer capacity also inside concrete for maintaining a passive layer. So what is the outcome? It is possibly you will see an increased carbonation depth at higher replacement level of SCMs. Okay, because there is no CH twice present to react with CO2. So CO2 will penetrate deeper inside concrete rather than getting reacted above, near the surface of concrete. Okay, so for chloride induced corrosion, SCMs has positive effect. Okay, but for carbonation induced corrosion, SCMs can have both positive and negative effect depending upon what is dominating, whether denser microstructure is dominating or lower pH buffer capacity is dominating. Okay, so more we'll understand about these two things when we'll talk about durability of concrete. But for now, just understand what is the effect of SCM. Now try to answer these three final questions related to durability, and then we'll conclude the session. Any doubt in this part? No. So just quickly answer question number 21. Which of the following SCMs would likely result in best balance between early strength and long-term strength? So which two SCMs I should combine so that I can have good early strength also and good long-term strength also? Can anyone tell me the answer quickly? So the correct answer for this will be B. Okay, moderate GGBFS with low silica fume. So silica fume will contribute to early strength, and GGBFS will also contribute a little to early strength, and GGBFS contribute to later strength also. So that's why correct answer will be B. A can also be correct, B can also be correct. Both can be correct. Okay. The carbonation rate of concrete is inversely proportional to which of the following properties significantly modified by SCM? Can anyone tell me the answer? Which of the following properties influences the carbonation rate of concrete when SCMs is added? So we saw this answer for this question just one slide ago. Okay, the correct answer is C. Just think about this. Okay, so tortuosity means the pore connectivity. Okay, so how connected the pores are. And so when we add seams to the in concrete, we are densifying the pore structure, so we are disrupting the tortuosity of pore structure, and which affects the CO2 diffusion. However, we know SCMs consumes calcium hydroxide, which can affect the pH of concrete. So that's why both are there. Tortuosity of pore structure and amount of free calcium hydroxide, they are both getting reduced, which can affect the carbonation rate of concrete. Question number 23. Degree of hydration in concrete with SCMs is critical for durability. Which of the following condition best promotes the hydration of slag in concrete? So, for hydration of slag, which condition, curing condition or concreting condition will be most suitable? So think about slag as a supplementary material. It has slow strength gain over time. So which property, like which condition I should give to concrete having slag so that it can suit its promotes its hydration, which is already a slow reaction. Okay, I will tell you the answer because we don't have much time. So correct answer is B. Why? Because hydration of slag is a slow reaction. So if I provide high curing temperature, the increased temperature will increase the kinetics of hydration, and it will promote early hydration. And prolonged moisture curing will ensure that there is no water loss from concrete. So hydration will continue to go on. Okay, we saw pozzolanic reaction requires water also in with along with calcium hydroxide. So if there is water present in concrete, it will promote hydration of GGBFS. Okay, so that's the correct answer is B. Okay, so this was all for today's session. We discussed about chemical admixtures. We had an overview of mineral admixtures and how they are produced, fly ash, slag, and silica fume. We discussed about effect of SCMs on cement hydration and fresh state properties like setting time, water demand, and SP demand. And we discussed about effect of SCMs on hardened state properties of concrete like compressive strength, creep, shrinkage, chloride corrosion, and carbonation corrosion. Okay. Now, if anyone has any doubt, you can stay back. And if you don't have any doubt,